All right, so I'm going to go over this practice final exam, and when I post this video, I'll also post the practice exam with the solution. So the final exam will be worth 20% of your grade. It'll be released basically Wednesday morning, and you have 24 hours to do it, basically during that Wednesday time period. And it's an open book exam. So you can use basically anything from this class, obviously your calculator, your notes, practice exam, homework, quizzes, any of that exam summary sheet, which actually I'm going to show you how to go create as I go through this, because a lot of people sent me lots of different things. I didn't realize that people didn't really understand that. So I'll give you kind of an idea. It should be basically like a bunch of equations and whatever. And I'm going to go over how to create one of those as I go through this exam. You can watch any of the YouTube videos I've made. OpenStax, the textbook, basically. Now, things you can't do. You can't work with other people. So I don't want to go through this exam and see two people with all the same answers and the same mistakes and things like that. So don't do that. Don't work with other people. Also, you can't just do, random Google searches for the problems or try to run it through some sort of program that will do the problem for you. Okay, so you're not allowed to do it's not completely open. It's open with our course materials. All right, so let's go through this. All right, so I've kind of already gone through this, but I'll kind of talk about things I think are relevant for the answers. So this is a linear equation. 3x minus 2 equals 22. Add 2 to both sides. 3x equals 24 divided by 3. That should be a pretty straightforward one for ones that we've done before. The second one now, it's very similar, except that you have to do this extra step here where you subtract the 2x. So you have to bring the x's to the same side, and you get 6x minus 2x is 4x divided by 4. All right. Number 3 is similar again, except you have to do a distribution. So this 4 gets multiplied to the 2x and the negative 1, and the 6 gets multiplied to the x and the 2. So you get these terms. You have to combine common terms. So in this case, you have two constant terms, so they get combined to negative 14. So I made a little bit of a mistake there, but I corrected it. And then once you get to that form, it's basically the same as this problem. Okay, so then move the x's to the same side, move the constant terms to the other side, solve for x. All right, and then we also have the symbolic version of that same thing. So when I do these, basically, if I circle my variable that I want, and then everything else I just treat as kind of a number that I don't know. So MGD, those are all numbers I don't know. So I'm going to group that together as kind of one number I don't know. And so I add that to both sides. I get T plus MGD, and I have FL. So in general, like if you have a variable that you want to isolate that term first by kind of getting rid of constant terms, moving constant terms away, and then I divide by f because I'm solving for L, and that's what I get. All right, so the trickier version of these is number 5 here. It's when the variable is on both sides. So just like when we had the 3x and the 2x and whatever, we try to move the terms that with the variable we want to the same side. So I'm subtracting Lx from both sides. And then this is kind of an important thing a lot of people mix up, is if we have nx minus Lx, this would be the same as if we had like 5x minus 3x. We know that this is 2x, right? But a way of writing this, which is helpful, is to think of this as you do 5 minus 3, and then you factor out an x. So that's essentially what we have here. We have the x's, and we want to factor out the x by just having n minus L. Right? And then we move the constant term to the other side, and then we divide by this factor. Right? So if you can put it in parentheses, you can treat it like a number. So that's the first thing when I was building my own equation sheet that I did, is I put this rule over here because I know that a lot of people have trouble with that. So that's the first thing that I added to my summary sheet. All right. Solve by the substitution method. So this first one is, this one's a little bit simpler than this because only one of the variables shows up in one of the equations. So first you solve this for x. So you subtract 5 from both sides, and then divide by -3, you get x equals 6. So a -18 over -3 becomes positive. So the negative over negative cancels. And then you take that x equals 6 and you plug it into this equation. And then you have this. So that's 12. And then you just subtract 12 both sides, divide by 7, you get y equals -1. So you get coordinate 6 and -1. So both of these are actually lines. And this would be where those two lines intersect on a graph. All right, so 7 is very similar, except x and y show up in both equations. So when that occurs, you have to solve one of them for solve for x in terms of y. So to do that, I just add 3 to both sides and get 2y plus 3 equals x. So I can't solve for a number at this point, but what I do is I plug that into the other equation. So it's 3x minus 5y, so 3 instead of x, I'm going to write what x is equal to, which is 2y plus 3. I have to distribute that 3. Let me just show that. So I get 6y plus 9. And I have 6y minus 5y. That gives me 1y plus 9 equals 7. Subtract 9, get y equals 2. And then, so I have y equals -2. To solve for x, though, I have to plug it back into this original relationship, 2y plus 3. So I plug in y equals -2. And I solve for x, and I get x equals -1, y equals -2. All right. So then we have converting between radians and degrees. So you're given 200 degrees, and you're asked to find in radians. So basically for both of these, it's the same strategy, which is that if you have degrees and you want radians, you multiply by pi and divide by 180. All right, so multiply by pi, divide by 180, and the idea is that the degrees will cancel, but you'll get your radians from this pi here. All right, so that's the next thing I put on my equation sheet, on my summary sheet here, is I put the conversion factors. So I have radians to degrees. Radians times 180 over pi gives me number of degrees, and then if I want to go degrees to radians, number of degrees times pi over 180 equals number of radians. And also over here I threw in these graphs to show me how angles, 0, 90, 180, 270, 360, and then 0, pi over 2, pi, 3 pi over 2, 2 pi, and then also I showed the kind of 45s, pi over 4s, diagonals as well. Because the next question is going to ask us to graph these things. So that's what I have here. Is you're given 135 and -90, and 135, 0, 90, 180, and then 135 is the diagonal. So 135, remember the angle is always measured from this positive x-axis, so that's the 135. And then if you get 90, you're basically going the opposite direction. You're going clockwise instead of counterclockwise. Counterclockwise is always considered the positive direction in many cases. All right, and then we have convert from radians to degrees. So we're given radians, and then what we do is multiply by 180 over pi, cancel out the pi, and then calculate this number, and that gives you 72 degrees. Negative pi over 4, again, to convert from radians to degrees, multiply by 180 over pi. And then you're also asked to graph some radian measures. So again, using this little picture that we had before, you can sort of figure those out. So this is negative pi, so that means we're going to go backwards. So negative pi over 2, negative pi is basically negative 180. 5 pi over 4. So 5 pi over 4 turns out to be one of these diagonal ones, so it goes all the way around over here. Okay. So yeah, so when I was looking at people's summary sheets last time, I basically gave almost everyone credit if it made any sense to me. But you know, people showed me all kinds of stuff, which made it clear to me that you guys weren't used to doing that, which is fine. But I guess I just assumed that you would know how to do that, which doesn't make sense. So then we have a bunch of like sine, cosine, tangent, SOHCAHTOA problems. So that was the next thing that I put on my sheet here. So I put all my SOHCAHTOA stuff right here. So SOHCAHTOA, sine is opposite over hypotenuse. Sine theta is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And I just drew a little triangle here to show that the opposite, adjacent, and hypotenuse for a right triangle. And I also threw in Pythagorean's theorem, and I drew little sketches of what the sine, cosine, and tangent functions look like. And this little picture here will come in later, and I'll tell you when we get to that problem. All right, so let's do this. So find the value of sine theta, cosine theta, and tangent theta in the figure. So sine theta is opposite over hypotenuse. So in this case, if this is our angle, then this is the opposite side, and this is the hypotenuse. Hypotenuse is also opposite the 90 degree, and this is the adjacent side to our angle. So sine is opposite 3 over hypotenuse, square root of 109. Cosine is adjacent over hypotenuse, which is 10 divided by square root of 109. And then tangent is opposite over adjacent, which is 3 over 10. Okay, so they ask us to find the sine of 60 and sine of 30. So we know that sine is opposite over adjacent, but since we have two angles, what's opposite is going to be different. So what's opposite the 60 degree angle is square root of 3 over hypotenuse of 2, whereas for the 30 degree angle, the opposite is 1 over 2. All right, so sine is still always opposite over hypotenuse, but depending on the angle you're given, you might have a different opposite. So this square root of 3 is opposite the 60, but is actually adjacent to 30. Okay, so you have to kind of be careful of this. So here, I'll just write opposite to 30 degrees, and this side is opposite to 60 degrees. So you have to be a little bit careful about that. Always think about what's opposite the angle or adjacent to the angle. And then it says solve for h using and then use sine, cosine, tangent. So what I did here is I basically did the Pythagorean theorem, which is a squared plus b squared, 3 squared plus 1 squared equals h squared. And if you square root both sides, you get h is square root of a squared plus b squared, which happens to be square root of 10. And then sine theta is opposite over hypotenuse, 1 over square root of 10. Cosine is adjacent over hypotenuse, so that's 3 over square root of 10. And then tangent is opposite over adjacent, which is 1 over 3. All right, so this is a type of problem that I think people had problems with when we had a quiz, but I give you a point 3, 2. And I say it's on the terminal side of theta, which just means that the angle of theta is in there. Draw the triangle, find sine theta, cosine theta, and tangent theta. So if you have this, I put this on my equation sheet right here. If you have one of these coordinates, x, y, this is your angle. Basically, those coordinates are going to be the x and y sides of your triangle. Okay, so we have basically a coordinate 3, 2. So x equals 3. And y is equal to 2. Okay, so in this case, here we find the hypotenuse. The hypotenuse is, so using the two sides, you can find the hypotenuse by doing the Pythagorean theorem. So this side is square root of 13. And then you can use sine, cosine, tangent. Opposite over hypotenuse, adjacent over hypotenuse, and then opposite over adjacent. And that's what I did here. 16, use trig functions to find the length of the sides A and C. So I start off with 50 degrees. So what I know is that this is the opposite side of that 50 degrees. This is the adjacent side, and this is the hypotenuse. So I just see what sine, cosine, tangent gets me. All right, so sine 50 is opposite over hypotenuse, so that's 8 over C. Cosine 50 is adjacent over hypotenuse, so that's A over C. And then tangent 50 is opposite over adjacent, so that's 8 over A. And so if I look at this equation, the only thing I don't know is C. And so I think we talked about ways of doing this, but I didn't really show the work here. But if you flip both sides, right, you get C over 8 equals 1 over sine 50, and then you multiply the 8 to both sides, and you should get 8 over sine 50. In fact, I didn't even calculate that yet. So 8 divided by sine 50, I get 10.44. And then cosine 50 has a over c, so I can plug in c and solve for a if I wanted to, but this one just has a in it. So again, what I would do is I'd flip both sides, so it'd be a over 8 equals 1 over tan 50, multiply both sides by 8, and I get 8 over tan 50. I get 6.71. Okay? And one thing you can kind of check is that the two sides should be less than the hypotenuse. The hypotenuse should be larger, so 10, 6.71, and 8. You can also use Pythagorean theorem. So if we use 6.71 squared plus 8 squared, those are the two sides here, and we square root it, square root our answer there, we should get 10.44. And we do. So that's a good check to make sure that was correct. All right, here's another one. Cosine equals, cosine t is 1/3 between 0 and 2 pi, so that means it's the first quadrant. Find the value of sine t. Assume the hypotenuse of the right triangle is length 1. So again, you have basically a right triangle. You have x and y sides, and your hypotenuse is length 1. So you're told your cosine t is equal to 1/3, and cosine is adjacent over hypotenuse. So if you look at that, what this means is that x is equal to 1/3. So your side of your triangle here, I'll just draw it real big, is 1, and this side is 1/3. Okay? So I think a lot of people had difficulty when they did this one because they assume that if it's 1/3, that this has to mean that this is the adjacent side is 1 and the hypotenuse is 3, but that's not true. It could just be a number. That's, a fraction. So in this case, the side is equal to 1/3. It's not even, the hypotenuse is 1, so obviously the hypotenuse can't be 3 according to this. So x is 1/3. And then you have to use the Pythagorean theorem to solve for y. So 1/3 squared is 1/9. 1 squared is 1. Y squared. Subtract 1/9 from both sides, and you get y squared equals 8/9. And then if you square root both sides, you get the square root of 8/9, which is the square root of 8/3. And then, so that's the y side, is square root of 8/3. And then you do sine, which is y over hypotenuse, y over 1, which is the same value. Square root of 8/3 divided by 1 is just square root of 8/3. And you can calculate that number if you want. Here, I'll just do it. So square root of 8 divided by 3. And that's 0.94. Okay. All right, so then there are a whole bunch of problems about graphical transformations here. All right, so I'm going to give you some function, and I'm going to ask you a bunch of transformation questions, basically. I'm going to give you the equation, and you tell me what kind of transformation, and then you graph the transformation. So what I did is on my equation sheet here, I just put every graphical transformation I could think of. So shift f of x minus h is shifting right h, and that means x goes, all the x values get changed to x plus h, and then x plus h inside the function shifts left. F of x plus k, if k is outside the function, shifts it upward. Minus k, if outside the function, shifts it downward. So if it's inside the function, it is going to be a horizontal movement, or horizontal change. And if it's outside of the function, it's going to be a vertical change. And then you have horizontal stretch and horizontal shrink. Oh, just let me point out again that the rules for x and y are reversed in terms of like minus and positive. So horizontal, 1/2 x inside the function is a horizontal stretch. 2x is a horizontal shrink by 1/2. And then so that's inside the function, that's horizontal. And then if it's outside, it's vertical. You see I made a little mistake there. But 2 stretches it by 2 vertically. 1/2 on the outside shrinks it by 1/2. And again, the rules for horizontal and vertical are flipped. Whereas you get a stretch for 1/2 x, you get a stretch for 2 f of x. So this 1/2 and 2 kind of the rules are switched for what 1/2 means when you're horizontal versus vertical. And then we have our reflections. F of negative x, if it's inside the function, is horizontal reflection. So that means you're going like this. And then negative f of x is a vertical reflection, which means you're going like this. Again, the negative is outside. And then the inverse function, you just switch x and y coordinates. All right, so that's what all of these are. So I'll give you a toolbox function. So x minus 2, so that's inside the function, so that's going to be a shift 2 to the right, and then plus 1 is outside the function, so that's going to be a shift upward. So when I did this one, all I did is I kind of like took these axes and I shifted them up 2, and I shifted, oh, did I do this backwards? I made a mistake here. Shift right 2, shift up 1. All right, so yeah, I did make a mistake here. I should have shifted this up only 1. I shifted it up 2 when I did this. Let me do a different. So this is like my new origin. So when I think of doing this, I have a 1 at 0, 1, and then 1, 2, yeah, and then 2, 4. And then I have negative 1/2, and I come in like this. So I should have looked like that. Yeah, I shifted it up too much when I did that one. All right. Then I have 1/2 x. It's inside the function, so it's going to be horizontal. And when I see a 1/2, that's going to be a stretch. So basically what I did here is I took these coordinates and I just doubled their x coordinate. So this is this one is 1, 2. So x equals 1 becomes x equals 2. So 1, 2 becomes 2, 2. So x equals 1 becomes x equals 2. X equals 2 becomes x equals 4. And you can see that basically it's the same pattern except the spaces between the... oh, did I make a mistake here? Yeah, this should be like this. All right, so I went through this practice exam faster than I should have, but basically the spacing becomes 2 for those points instead of 1 earlier. So when I do these also, I think it's really important, I think I mentioned this in one of the reviews we did, is to use like relative points. So here we have a 1/2 on the outside, so that's going to be a vertical shrink. So basically the y components get cut in half, right? So all the y values get cut in half. So for example, this was 0, 1, but now it's 0, 1/2 because it's half the value. This was 1, 2, now it's 1, 1 because 2 and half is 1, etc. So all those numbers kind of come close to the axis like that. 2 to the negative x, that's a horizontal reflection. So basically it gets flipped like this. So it used to go up like this, but then it's going to get flipped, so it's going to go like this. So basically one of the ways of doing this is make all the values of x go to negative x. So also the vertical shrink, all the y's go to, this is by half, go to 1/2 y. All right, and then you have the inverse function, and basically what you do is you just switch all the x and y coordinates, okay? So if it was 0, 1, it becomes 1, 0, right? And then 1, 2 becomes 2, 1, etc. So all the x and y coordinates get flipped with each other, right? So here, I'll just give you an example. So we had one that was x equals 1, y equals 2. That got turned into 2, 1. So the x and y values switch places, and that's the inverse. So you'll have one of these will be, a set of these will be trig functions. So here x, cosine of x minus pi over 2 plus 1, so that's going to shift to the right, pi over 2, and shift up by 1. So what I did, yeah, right. So what I did is, again, you can kind of think of this as you take your function here, and you can redraw your axes. And you can take these axes and shift it to the right, pi over 2, and then shift it up 1. So this is your new axes, and then you can redraw it. So remember, from this shape, you start at a peak, and it goes down, and then it goes down. So these cosine functions go on forever, so it always follows a pattern of like 0, up, 0, down, 0, up, 0, down. So you can just kind of, you draw that portion, and then you can kind of just trace out the rest as kind of going, up and down every pi over 2. All right, here we have cosine of 2x. So when you see the 2x in the function, that's going to be a horizontal compression by half. So basically what happens is that like all the x values get divided by 2. So what that does is here this point is pi over 2. So that point becomes pi over 4. So that point moves in halfway. This point is pi, so that moves into pi over 2. Okay, so you get something like this. So this point over here was this point over here at pi. It gets moved into pi over 2. And then that point was negative pi. It gets moved into pi over 2. And then, yeah, so this point, it was at a negative 1 over here at negative pi, and it got moved in to negative pi over 2. And so you can kind of draw that one. But then you also know that it kind of follows this pattern of, up 0, down 0, up 0. So you can kind of continue it on with the same frequency, as it's called. All right, so basically it does kind of like this kind of top to bottom between 0 and pi over 2, so it's got to do kind of the reverse between pi over 2 and negative pi, and so forth. So the whole thing gets kind of squished in closer together. Did I put something like that on my equation sheet? Oh, yeah. Next stuff is even and odd stuff. All right, so I mean, these are kind of similar. A vertical stretch, so I just make the y values go to 2 times. Vertical reflection, the negative sign's on the outside, so that means that y goes to negative y, and negative y goes to positive y. And then the inverse here, you have to be somewhat careful with these, but basically what happens is you switch x and y. So for example, we had a point which was 0, 1 for the cosine function, so that becomes 1, 0. So that's what this point is over here. And it goes like this. So we don't go down here, even though it's really like just kind of a sideways sine function that goes like this. But we limit it so that it remains a function. So remember that if it's a function, you can't draw a vertical line and cross the function more than once. But if I kind of started going backwards, then you could see that I would cross the function more than once with a vertical line. That means for one x value, there should only be one y value. But if it went like that, there'd be 2 y values for a particular x. So we limit it. These are kind of tricky, but one way of kind of visualizing it, I'll draw it with a pencil, is to think about like what the regular one would look like, and the regular one would look kind of like this. And it should be kind of symmetric about this diagonal. All right, so I'm going to erase that so it's not too confusing. But you could kind of draw it and then think about like if it got reflected about that diagonal, which way it would look. Because sometimes kind of figuring out how it's going to curve is kind of tricky, but it should be a reflection about that diagonal. All right, so we're about halfway through this. All right, so I drew one of these in, which is basically, I'm going to give you one of these cosecant, secant, cotangent, tangent functions. I'm going to ask you to do the same sort of thing. So this one's a cosecant. One thing is a cosecant is 1 over sine. Did I include that here? Okay, so I threw it on the bottom here because there's some graph stuff down there. But cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent. And I just sketched some of those pictures. But one of the things about the cosecant is that if you draw the sine function, is that it just kind of kisses the peaks and the troughs, and then it kind of goes up toward infinity on the opposite directions. So if you know what the sine function looks like, you can kind of just kiss it off there. So here we have a shift, minus pi over 2 plus 1. So right pi over 2, up 1. So I shifted our axes, and then I redrew my cosecant function from there, right? So this would be like the pi over 2, 1 point, which is this one. Right 1, up 1. and then left 1, down 1. And then I had to draw an extra one. And again, the pattern for these is basically like it goes kind of like you have an up and then a down, and then an up and a down. And it just kind of keeps it with like you up and then you down, you up, you down. And it goes on forever. So you just fill in the rest of your range with whatever following that pattern. We have a horizontal shrink by 1/2. So instead of this original one going from 0 to pi, that's going to be shrunken in. So it only, the same U shape, but only between 0 and pi over 2, which is what I drew over here. And then I kind of continued the pattern to fill in the rest. So this one, negative pi, it was like a big U, but it gets pushed in, so it's like this. So horizontal shrink is x goes to half x. All right. You have the 2 is on the outside, so that's a vertical stretch, and so basically that's y goes to 2y. So instead of kissing at this point here, pi over 2, 1, all the y values get increased get doubled. So instead of being 1, the y value goes from 1 to 2, and it goes from -1 to -2. And then we have the negative cosecant is a vertical reflection. So you basically just take it like this and you flip it over, right? So we had a U over here, and then it got flipped over. And we had a U down here, and that got flipped over. All right. Now, this one was kind of tricky, but the inverse function of this between negative pi over 2 and pi over 2, I corrected this on the one I'm going to give you. But basically what we want is we restrict it to like just this portion right here. We restrict it to this part that goes up and this part that goes down. And again, when you do the inverse function, you just sort of flip it by the diagonal. So instead of kind of following the y-axis, it's going to follow the x-axis. And here, this portion over here kind of goes toward negative y, so then it's going to go toward negative x. And when you do that, you should get something like this. All right? And again, it should be something that kind of is a reflection about the diagonal, right? So the other one, the original one, kind of looked like this. And you can see how that's kind of a mirror image. Okay, so that one's definitely tricky. These can be tricky. That's for sure. Hopefully that makes sense. And then the last one of these, you'll probably be sick of these by the time you do them, but I'm just going to give you kind of like a random function of straight line pieces. And it's basically the same idea. We have x plus 2 plus 4, so that's 2 to the left and then 4 up. So you just shift those points 2 to the left, 4 up. We have a vertical stretch by 2 because the 2 is on the outside of the function. So vertical stretch by 2 means y's go to 2y. F of 2x, that's a horizontal shrink. So that means x goes into half x. So all the x values get divided by 2. And then we have f of negative x. It's inside the function. The negative sign is a horizontal reflection, which means we're going like this. So all the x values get turned into negative x, and also the negative x values get turned into positive x. So here we had some negative values in the original. Those get moved over to the positive side. And then the inverse again is you just switch x and y coordinates. So I think in the original we had a point that was -3, 1. And that gets switched to 1, -3. So the negative signs stay with their numbers. They just switch places. Sometimes people mix this up by changing the negative signs, but you don't do that. You just switch the numbers. X gets switched with Y. Okay, and then we have inverse stuff. What did I do with that equation? Should we do it over here somewhere? Oh, I put it, it's on the bottom here. Yeah, so inverse stuff. I put a bunch of inverse stuff on here. So I have even and odd, which is actually the next question. So even is f of negative x equals f of x. I have the odd condition. And then I just put a bunch of stuff to show, like if I have a function, how I solve for the x in the function, which I do the inverse function of both sides, which gives me f of x equals a. So x equals f inverse of a. This should be a. Okay. And then I have e to the x equals a. If I want to solve that, I take the natural log of both sides, and that gives me x is natural log of a. X squared equals a. Take the square root, so it's x equals plus or minus the square root of a. So this one you need to do plus or minus when you do square root. Ln of x equals a, so you take the e to the x of both sides, so x equals e to the a. Sine x equals a, x equals sine inverse of a. Cosine x equals a, x equals cosine inverse of a. Tan x equals a, x equals tan inverse of a. So if you have any of these within the variable you want on the inside, you have to take the inverse function of both sides. And that's what these next set of questions. So the first one is find the inverse of this function. So the first thing is f of x gets turned into y. Then you switch x and y. That's inverse always switches x and y. Solve for y. And then y is f inverse of x. Okay, so you have this -3 in the denominator. I'll accept this. But if you want, you could just multiply the top and bottom by -1, which would flip the order of the top and make the 3 positive. All right? You're given some function like this. You want to know if even or odd. So what you do is you solve for f inverse of x. So you replace everywhere you see an x, you replace with -x. And when I do that, I take this negative sign in front is -1 over x. This negative sign in front of this term, so that's -3x. And then I compare it to f of x and compare it to negative f of x. So negative f of x is negative times this. I distribute the negative sign. I get -1 over x minus 3x. And f of negative x and negative f of x are equal. So that means that it's odd. This inverse function, I have this e to the x equation. So the first thing I'm going to do is going to solve for e to the x, add the constant term, subtract 2e to the x to both sides, so I get 3e to the x. And then divide by 3, and I have e to the x equals 9. To solve for x, I have to take the natural log of both sides. So natural log of this side equals the natural log of this side. So as long as I do that same procedure to both sides, they'll still be equal. Ln of e to the x, there's an inverse function, so that just gives an x. And I have log 9 on this side, so that's my answer. All right, we have this x squared equation. Again, solve for x squared, subtract 1, divide by 4. X squared equals 2. Take the square root of both sides. Square root of x squared is x, and then plus or minus square root of 2. So include a plus or minus for square root. That's kind of an important one. We have 36 minus 5 ln of x equals ln of x. So add ln of x to both sides. Solve for ln of x divided by 6. So we get 6 equals ln of x. Take the inverse function of both sides, which is e to the x. So e to the left side equals e to the right side. E to the natural log of x is just x because those are inverses. So this side is x, this side is e to the x. So x is equal to e to the 6th. All right, and then it says use the tan inverse function to find theta. So tan theta is the TOA part, is opposite over adjacent. So tan theta is 3/2. Take the tan inverse of both sides if we want to solve for theta. And tan inverse of tan theta is just theta. Tan inverse of 3/2. So I didn't calculate it yet. But under these calculators, you do second tangent, gives you a tan inverse. And then 3 divided by 2. I get 56.3 degrees. All right, then we come to a section on oblique triangles, and I also included some oblique triangle stuff here. So I included the law of sines. So I drew an oblique triangle. I did the law of sines. So remember when I did this, the capital letters are angles, and then the small letters are sides. And remember, capital A is always opposite A, capital B is always opposite side B, capital C is always opposite side C. Law of sines, sine A over A, sine B over B, sine C over C. So those are equal to each other. I also threw in the law of cosines. So there are 3 ways of writing it where basically you just switch the two, you switch 2 of the things. But remember that whatever's on this side its angle has to be in this cosine. So side a squared has to have angle a inside this cosine. If you do this for b squared, then it has to be cosine b. C squared is got to be cosine c. So that's what it is. So what they gave us is they gave us two angles and a side. This is a classic law of sines. So you can use this angle with its opposite side, that's sine A over A, and this angle and this side, that side we don't know, sine B over B. So basically when we set it up, the only thing we won't know is B. And then I flip both sides and multiply sine 37 to the other side. I get 100 sine 37 over sine 48. Let's call that 81 degrees. I mean 81. Yeah, that's a side, so there's no degrees. So that's 81. All right. Law of cosines for side B. So since we want side B, we're going to use the version of law of cosines where b squared is on the outside here. A squared c squared minus 2ac cosine b. So this b has to line up with this b. So we have basically everything on this side. So just square root it to solve for it. And square root is usually a plus or minus, but I want a positive length for this triangle. So, and again, I didn't calculate any of this, but all of this you can put in your calculator as one long line. So 6 squared plus 8 squared minus 2 times 6 times 8 times cosine 32, and then close parentheses for that square root. I get 4.3 as my side of that triangle. All right. So usually if you're looking for a side, that should be the one that you isolate by itself on the left side. If you're looking for an angle, then you'll have to put it over here and then solve for cosine. Okay. I don't know if I put anything on here for components. Oh, I did. For components, I added x equals r cosine theta and y equals r sine theta. So those are basically the components here. One thing to remember about these components is if you're going to use these equations, you have to use the full angle from 0 degrees right here. So I give you the 60, but you should use this full angle if you're going to use this. If you want to draw like a smaller triangle, like it's also possible, here I'll just draw it on the side, you could do something like this, where you know this is 60 degrees and this is 20, and you can solve for x and y. But if you do it if you use a smaller triangle, x would be 20 sine 60 and y would be 20 cosine 60. You have to put an extra minus sign in for x because it's going to the left. Whereas if you use the full angle, it'll come out automatically. So here I'll use 20 cosine 150, negative 17.3. And then the y value is 20 sine 150. I get 10. All right. So we go 10 up and negative 7.3 to the right. All right. I threw in one of these, which is, this is for the quadratic function. And I asked you to find the vertex. And basically the vertex, if you have this form, this is the a equals x minus h squared minus k. The vertex is basically this number and this number. But you just have to be careful remember that x minus 3 is a shift to the right, and then it's negative 2 down. So if you go right 3 and 2 down, your vertex will be at 3 comma negative 2. Okay, so there's a negative sign already in here. So if you see a minus 3, that means h is 3. If it's plus 3, that means if it's x minus h, you have a double negative, so h has to be negative if you see a plus in that position right there. Find the vertical and horizontal asymptotes. So that's something I also put on this equation sheet, which is this. So the vertical asymptotes are when the denominator equals 0. Horizontal asymptotes is you keep only the highest order terms, and you have something like ax to the n over bx to the m, n greater than m, no horizontal asymptotes, n equals m, your horizontal asymptote is a over b, which is whatever those coefficients are, and then n less than m, the horizontal asymptote is equal to 0. So that's what we're going to do. So the first one is vertical asymptote. It makes the denominator 0. X minus 2 is 0. So vertical asymptote's at x equals 2. And then the horizontal asymptote, I just keep the highest order term. So I have 3x minus 3. Here, I'll just write it. 3x minus 3 over x minus 2. And if I only keep the highest order terms, I'm only going to keep the 3x and the x. So it becomes 3x over x. And you can see these are both x to the power 1. So that would be the condition where they have the same. So this basically cancels out and you get 3, right? And so the horizontal asymptote is at y equals 3. And just remember why we keep the highest order terms, because this is as x goes to infinity. So as x goes to infinity, it's only the highest order term in here which is going to matter. You can just say approximately the rest of the terms don't matter. So if the highest order term is x, x is going to be, when x approaches infinity, is going to be much greater than negative 3. Let's say there was an x squared here. You know, here, I'll just write it as a side here, and I'll erase it. Let's say it was x squared plus, let's say it was 2x squared plus 3x minus 3 over x minus 2. So if that were the case, if x goes to infinity, x squared would be much greater than this, so you get all rid of everything. We just keep whatever's in front there with the highest power of x, 2x squared over x, right? In this case, this would be a case where n is greater than m. This is 2 over 1. So this would be no horizontal asymptote. All right, I'll erase that so when I scan it, people won't be confused by that. And then we have our last two are, I threw in some of this calculus stuff, but basically I give you a function. I didn't give you a hard one. It's basically just a linear function. And I asked you to do this, right? So again, if you see this, do it in pieces. First, find f of x plus h. So it's a composition of x plus h inside of this function. So 3x minus 5 becomes 3, and then x plus h minus 5. Solve for that. Then do f of x plus h minus f of x. So here, this is our f of x plus h from there. Minus f of x, I distribute this negative sign. So it becomes negative 3x plus 5, and I get cancellation. 3x cancels out with negative 3x, negative 5 cancels out with this plus 5, I get 3h. And then I do the next step, which is I take that and divide it by h. When I divide by h, the h cancels, I get 3. Limit as h goes to 0 of 3 is still just 3. I guess I could show another step. Limit h goes to 0, which is also 3. All right, so we did some where there were still h's in here. Like if it was plus h, you just ignore that and just keep whatever number. That's what it is. So this is the derivative. The derivative function of this is a straight line. It always has a slope of 3 no matter where you go. So this derivative is always 3. And then the integral, negative 2 to 4, remember, is the area under the curve. So it goes from negative 2 to 4, and I shade in between the x-axis and the function. And if it goes below the axis, that's a negative area, and above the axis is a positive area. So we have our positive triangle area, which is this, minus our negative triangle area, which is this. So I calculated those, and I got 6. So this is mainly just your ability to interpret the meaning of this integral, which is area between the curve and x-axis, and determining the area of triangles and knowing that if it's under the x-axis, it's going to be a negative area. All right, so there are 50 questions. Each of them are 4 points, and you'll have basically an entire day to do it. You can use any notes we have. You can even use this video. So as you go through it, you can use this video. The problems will be different, but it might be helpful. If you have any questions at all, please send me an email. Let me know. That's it. Thanks a lot. Let me know if you have any issues at all.